Well, thank you very much for the nice introduction and for the opportunity to speak here today. So what I'm going to talk about here is this is joint work with Leah Rebholz of Clemson University, and I'd like to acknowledge the support of the National Science Foundation. Okay, so since I'm kind of a newcomer to the numerical linear algebra community, I wanted to just do a quick intro to some of the work I'm doing. So I basically have two projects going on right now. This first one that I'm going to talk about today is on some theory behind Anderson acceleration, and I'm working on this with my students Matt Dallas and also Simon Cato. He's an undergrad. I've been working with him for a couple of years. He just graduated this past weekend, and he's going off to grad school. And then my other main work is on extrapolation methods for matrix and tensor eigenvalue problems, and I have my student Ria working on this with me. Simon's also done some work on this. He was working specifically on the PageRank problem, so I'm looking forward to hearing the next lecture from Yosef. Right, and so we're going to focus on this project today. Oops. Okay, so yeah, so first I'll go over a quick introduction to Anderson acceleration and the algorithm, and we're going to look at some questions that actually come up with the method. And then go over some recent theory, and then how we use some of these theoretical advances to improve performance of the algorithm. And I'll illustrate this with some examples. All right, so the basic background is we're thinking about doing a fixed point iteration, where we have some complete norm vector space or Banach space, which we'll call X. And we'll assume that our fixed point operator phi is Lipschitz continuous with this constant kappa. So of course, the fixed point problem is to find x such that phi of x is equal to x. And a common way to find such a fixed point is a fixed point iteration. We start with some element in x, and we said xk plus 1 is equal to phi of xk. And the error analysis is pretty basic. The error in the k plus 1 iteration can certainly be bounded by kappa times the error in the kth iteration. Now, if this kappa is less than 1 and a lot less than 1, this is really super, because it means our fixed point iteration will converge and converge pretty fast. If kappa is less than 1, but not much, then it's not that. I mean, it's super in the fact that a unique fixed point exists, but it's not so super from a numerical perspective, because it doesn't necessarily mean we'll converge, this week or this year. And if kappa is greater than 1, which is often the case, it doesn't mean we'll converge at all. It also doesn't mean that we won't, and so often we do a fixed point anyways, just to see what happens. But the goal of these extrapolation techniques are to improve the efficiency and the robustness of the iteration. And the idea is to do this using a history or memory of previous iterates to improve the approximation. All right, so here's the Anderson acceleration algorithm. Maybe I might get better from this side. All right, so here's our fixed point iteration. We have xk plus 1 is equal to phi of xk, which I like to write as xk plus wk plus 1, where your wk plus 1 is your update step. But of course, you can also write it like this, where wk plus 1 is phi of xk minus xk. So we also sometimes just call it the residual. So this Anderson iteration with depth m is, first we set a maximal depth m. We do our initial fixed point iteration, and then for subsequent iterates, we compute our update step. And then we solve this little optimization problem, where we find the best representation of W, our most recent residual, in the space, the column space of these differences between consecutive residuals. Then we go ahead and set a damping or mixing parameter. If we don't want to use damping, we just set that to be 1. And we perform our update, which looks like the standard fixed point update, plus a correction step, where our correction step, we have the difference between consecutive iterates, which is in this matrix EK, and the difference between consecutive residuals. And we just take those in the linear combination given by this, this optimization coefficient gamma. So here to keep a few things in mind, these matrices, EK and FK, they each have MK columns, but we don't need M to be constant throughout the entire iteration. Often we will say that MK is equal to the minimum of K and M. I'm going to argue it's less than equal to the minimum of K and M. We might not want to use all columns available. And finally, we're going to define this theta as the gain from the optimization problem. Clearly, the norm of this is less than equal to W, because if all the columns of F were orthogonal to W, you would just take this gamma to be 0, and you would get the norm of W here. So this theta is never greater than 1. So here's a motivating example. So this is a Picard iteration for a steady Navier-Stokes. I won't go into detail about this. It's a finite element discretization, but when the Reynolds number is sufficiently low, the iteration is contractive. When the Reynolds number is sufficiently high, you're in a more turbulent regime, and the iteration is not contractive. So in the contractive regime, here we're applying Anderson just with simple depths 1, 2, and 3, and you see it actually does improve the convergence rate. When we apply it with this higher Reynolds number, where in fact the iteration is the Picard iteration is not contractive, even with depths 1, 2, and 3, we still actually see what looks like linear convergence, but only if you kind of stand back and squint at it. But if you look more carefully, you see us wiggling up and down here. Here's another example. It's kind of the same example, except now we're applying Anderson to a Newton iteration for the same problem. And a couple of interesting points here. So here, with a low Reynolds number, Newton is converging very nicely, and it's this red line here. If we apply Anderson, and here we're just doing 1, 2, and 3 to the Newton iteration, we're actually still converging, but you see we're not getting a quadratic convergence. We're actually getting a superlinear convergence. So, you know, we've made things worse, so we don't necessarily want to do that. But in this slightly higher Reynolds number, here you have Newton is not converging, it's diverging very nicely, as it likes to do. Usually what we would do is a line search, which is this red line going down here. But the other lines we see are again, Anderson 1, 2, and 3 applied to Newton, and we see actually they are also converging very nicely, which gives us a couple of observations. One is that Anderson applied to Newton, well, it's superlinear, but it's subquadratic, and this is true whether you're applying it to the Picard or to the Newton. And two, in the second diagram, it's actually doing something similar to damping outside Newton's domain of convergence. So it's actually improving the domain of, enlarging the domain of convergence for the Newton iteration. That's something we don't entirely understand yet. And my student Matt is actually working on the Anderson applied to Newton iterations in certain circumstances. So here's a little history behind the method. It was introduced in 1965 by Donald Anderson. He called it the extrapolation method, but we tend to call it Anderson acceleration now. A couple of nice papers are in 96 and 2009, which relate the Anderson to the generalized Broyden and multi-secant families of updates. This 2009 paper by Yusuf is one of my personal favorites. And here, one of the things that they do is they express this optimization problem posed as the least squares problem. Now, you wouldn't actually want to solve it in terms of the normal equations, but if you can write it down that way, and that's how you actually get the relation 2 to the Broyden. And in fact, the way I wrote Anderson here is to the type 2 or to the bad Broyden method. There's also a version that relates to the type 1 Broyden method. So what I'm going to talk about more today is that if instead of writing it down in terms of the normal equations, if you write this down in terms of a QR decomposition of your matrix that you're using for your least squares problem, you can analyze the QR factors, and this will actually give us some insight into the convergence behavior. So this other important paper in 2011 by Walker and Nee, where they're looking at results on electronic structure computations, they also give a discussion of efficient and robust implementations and do several examples outside of electronic structures. And I think it's this paper that really brought a lot of popular attention to the method that we're currently seeing. So about 50 years after this method was introduced, we actually got the first convergence analysis. And this is by Tim Kelly and his student at the time, Alex Toth. And they showed local convergence for contractive operators. Now for m greater than 1, they assumed a boundedness of the optimization coefficients. And this became a rather standard assumption. Today, we're going to look at how we can avoid this assumption and actually safeguard against it using this filtering strategy. So what they essentially showed is they showed that asymptotically, the convergence rate is no worse than that for the underlying fixed point iteration, which I'd like to emphasize was a pretty huge result because there really wasn't such analysis for the first 50 years. So our work, which was first for the study Navier-Stokes and then for more general contractive fixed point operators, showed acceleration theory that actually shows that you do improve the convergence rate at least locally. The work I'm going to show today builds on that, and I never liked how we dealt with the higher order terms in this work because we did a Cauchy-Schwarz inequality that I really felt threw away a lot of important information. Here we can recover that information, and we can see how we can replace the boundedness assumption by this filtering strategy. And we can also do a one-step analysis that holds not only for contractive, but also for some non-contractive operators. So this method is, well, it's very closely related to nonlinear GMRes. And it's also or a very close variant is known as a Poulet mixing in the computational chemistry literature. And there's been a vast literature that's rapidly increasing. So my recent interests have been on adaptive parameter selection and on Newton-specific theory.
Question?
Yeah.
A comment actually.
Oh, that was Poulet.
Yeah.
Yeah, he was talking about the electronic structure theory. That's interesting.
Sorry.
No, I'm glad you're taking the chair though. So some. Oh. And now we all know how to pronounce Lansoch. Lansoch? Well, luckily it's not in this talk. So, so some questions that naturally come up here are, first of all, when should we even use this acceleration? How do we set the damping? How do we set this algorithmic depth? Often in the literature, it points out that this least squares matrix can go bad in the asymptotic regime, or that it might. And so the question is, do the columns become more linearly dependent as iterations continue? And can we improve the iteration by selecting which previous steps to use? This one's highlighted because I want to talk about it more. But just some quick answers. Well, one, it's more of an essay question, so I did not include it in the answer key. But basically, we should use it when Newton is either not working, if it's undesirable, either analytically or computationally to form the Jacobian, or if we can form it and it's just not converging, or if it's converging poorly. Then we might want to think about accelerating a fixed point iteration or accelerating Anderson, Newton. 2 and 3, the answer I'm going to argue and hopefully convince you today, the answer is dynamically. We want to adjust these parameters as we go, and we want to see how to do that. 4? Not necessarily. In fact, what we'll see is that these columns, they tend to have their linear dependence problem at the beginning of the iteration, which is why that's where the safeguarding really tends to be more necessary than at the end. And in fact, yes, we can improve performance by being selective on which columns to use. My little extra credit question is, what does this picture have to do with filtering? So several of the techniques we use to improve the performance, my cat illustrates very nicely, but I wasn't exactly sure how she does filtering. And then I realized she kind of embodies it by really ignoring everything that I say. But also you notice the sun is filtering very nicely through the leaves here. So this is my representation of filtering. So what I'll show you today is really this one-step residual bound and what we can learn from it. So what it says, and this is based on some conditions that we're about to talk about, is that the norm of the residual for the k plus first step is bounded by the norm of the residual from the previous step times these factors here, which by the way would be precisely what you would have if you just did the fixed point iteration with the same damping factor, except that here it's modified by this theta k, which was this gain from the optimization problem, which is no greater than 1, but you pay a price. And this is all the higher order terms in here. So a couple of things to see about it. First of all, the higher order terms are multiplied by this square root of 1 minus theta k squared. Something interesting about this is that if your optimization problem totally failed, so that would mean the columns of fk were actually orthogonal to wk plus 1. Okay, so then this would be 1, but then this would be 0. So you actually wouldn't be paying a price at all. Where you do tend to pay a price is where that this is maybe not too small. And if this constant is big, and if your residuals are big, which means that when these higher order terms multiply each other, they actually add up, and then that's bad. So one thing we're going to see is about how we use filtering to control this constant c over here. Okay, so really the proof is in 2 parts, and for this first part we're going to make some smoothness assumptions. First of all, that our fixed point operator phi is Lipschitz, and that we have it's continuously Fauché differentiable, and kappa hat is the constant, the Lipschitz constant for the derivative. Now, it's not true that you actually need your operator to be this smooth to run Anderson acceleration. So here what we're doing is we're just doing some Taylor expansions and triangle inequalities to rewrite our residual bound like this. Now you could, I think in principle, actually use the generalized derivatives in the sense of Clark to do a similar Taylor series like expansion without all the smoothness. There's other approaches to also analyzing the behavior of Anderson without smoothness, and I think Tim Kelly is doing some interesting work on that right now. But for now, we're going to assume we have such smoothness, and we do our Taylor expansions and triangle inequalities, and we get this. So we get from the first line to the second. Here, we're just applying the definition of this gain factor theta. And then we've almost got our bound. The only problem is that here our higher order terms are written in terms of the difference between consecutive iterates, which are the EJs. And we really like them to be in terms of the Ws, which are the residuals. And that's where most of the technicality actually comes in. But it so happens we can relate the optimization gain and coefficients. So here what we have is the fixed point, the update we have before we have our fixed point update plus our correction step, where again the EK is, this is our matrix of differences between consecutive iterates, and FK contains the differences between consecutive residuals. So now let's suppose we're in a finite dimensional Hilbert space, which is going to make life a lot better. And of course, the way we do this computationally is just by doing a thin or economy QR decomposition to solve this least squares problem, to find the best representation of W in terms of the columns of F. So now we actually want to use this QR decomposition in our analysis as well. So here we can just write out gamma, our vector of optimization coefficients, in terms of the QR factors. And then that gives us the norms of the best represent the W minus FK gamma in terms of, this is how we defined it in terms of a theta times the norm of W. And it also gives us this norm of Q transpose W is then bounded by the square root of 1 minus theta squared times WK. And you'll notice that when we take norms of this above and plug in the QR factors, this is going to do most of the work for us. I'll also mention that here we can now compute theta as soon as we've computed our QR factors, in particular the Q. And this can be useful because it means we can use it to define our damping factor beta. So we can choose beta based on theta and then assemble our whole fixed point update. So just plugging in the QR factors to the update here, we get this bottom line over here. All right, so just a reminder, our goal is to close this first residual bound, which means we want to write these E's in terms of the W's. So from what we had on the last slide, which is here, we just take norms, which gets us here. So we've got almost everything except we have this norm of this EJ RJ inverse, where E is the matrix that has each column is a difference between consecutive iterates, and R inverse, this is R of the QR decomposition of F, which has the difference between each column is the difference between consecutive residuals. So the interesting thing is that we can see this is bounded by a constant under a couple of conditions. So this first condition here has more to do with the fixed point operator itself. And it says that there's some constant by which the ratio of the norm of the difference between consecutive residuals over the difference between consecutive iterates is bounded away from 0. Now this is clearly satisfied if your fixed point operator is contractive, if this cap is less than 1. Another circumstance in which this is satisfied is if you think about our fixed point operator, if we're using it to find the 0 of a function f, then in fact, all this says is that the smaller singular value of f prime, the Jacobian of f at x, is bounded away from 0 in the vicinity of the solution. And this is naturally satisfied, at least locally, in the vicinity of the solution, which is, and this interpretation also makes sense because we already know that the method is essentially, it's a type of quasi-Newton method. So you'd expect some sort of Newton-like non-degeneracy condition to give you something useful, and it does. Now the second condition, it looks a little strange, but it actually makes sense. So if you think about doing this, if you only had a depth of m equals 1, you would only have one column. And then the question is, well, what happens if you have more columns in this matrix you're using for your least squares problem? Well, you could essentially just write out the solution in terms of doing like a Gram-Schmidt factorization. Of course, you'd really want to do modified Gram-Schmidt, but you can still think of it in terms of you could write this out. And so really the problem is you have to somehow encode to what extent the columns of F are becoming linearly dependent. And so in fact, what we need is there's some constant, we'll call it CS, that bounds away from 0 the direction sign between each column of F and the columns to its left, which is where we're keeping the more recent iteration. So in fact, this is precisely the information we have in the off diagonal entries of R of the QR decomposition. So this is something we can easily check because we've already computed what we need, and this is what we can use to filter out columns we don't want, and that's essentially the filtering strategy. So we can call this a sufficient linear independence condition. Or enforcement, and this actually replaces the assumption that the optimization coefficients are bounded. So this next part might look a little fancy, I don't usually present it, but I figured this is, since we're talking about linear algebra here, numerical linear algebra, it fits right in. So we just want to see how much the columns of F not being orthogonal messes things up, and how we can bound this norm of E times R inverse. So to do this, we needed this, this little lemma on the inverse, the entries in R inverse, where R is of the QR decomposition. I actually assume this must be a known lemma, but I didn't know where to find it. Maybe somebody here could tell me. All right, so we're writing the SIJs are the entries of R inverse here, which is the R of the QR decomposition of F. And essentially what we need is that the entries of these S's are bounded by the reciprocals of the norms of the columns of F, and some factors involving CS, which is our lower bound on the directions of signs between each column and the subspace span to its left. And then CT is just the bound on the corresponding direction cosines. And we can, I'm not showing the proof here because it's actually not that interesting. It's just a simple induction argument. So then the way we can put all this together. All right, so we're writing R hat is just RJ, and S represents R hat inverse. So first we can expand our EJ times R inverse just in terms of its columns. And then so it really suffices to just bound the norm of each column, and that's just bounding the 2 norm by the Frobenius norm here. So for the first column, we just apply the lemma. And now each column of F is a difference between consecutive residuals. So 1 over the first column of F is just 1 over times this norm of WJ plus 1 minus WJ. And so here is how we're actually using this first condition here. So this is going to be bounded by sigma times we can bound all this stuff in here by this expression here. And how we're simplifying is we're really just using some finite geometric sums and some binomial expansions. And then for columns 2 to m, we can essentially, we just use the lemma, and we get this bound over here. And then we just need to add up all the columns. So if we don't have all the columns are orthogonal, well, we can add these up here. And you see it's a little upsetting that you have a CT in the denominator, because if the columns were orthogonal, then this is 0. And if they're nearly orthogonal, this is nearly 0. And then, but it turns out that if you then go ahead and expand this, you can write it like this. And there's no CT in the denominator. It's really fine. If the columns are orthogonal, you can just use this directly and plug in CT is 0 and CS is 1. And you would get that the bound is m over sigma. If the columns are not orthogonal, so CS is less than 1 and CT is greater than 0, then this is bigger than m over sigma. But this is basically how, if you filter out the columns for which to get a sufficiently high CS, the CS if you're choosing, you're then going to control this this constant C over here. And that's really kind of the technical details behind this. So this is essentially the slide I had before. So we have this bound on the most recent residual in terms of the previous residual. This first order term gets decreased by this gain factor theta k. And then the higher order terms, they add up here. They're multiplied by the C and this 1 minus theta k squared. So now we want to talk about how we actually use this in practice. So if I want my first order term smaller and the residual is large, well, then I don't want to increase my gain factor, because I don't want to increase the depth, which could decrease the gain factor, but it would be outweighed because my higher order terms would pile up and I wouldn't converge. So instead, that's where I really want to choose my, my damping or relaxation factor. And I can do it based on the gain factor. For instance, one strategy, if you can approximate this Lipschitz constant kappa, you can just solve for beta such that this whole factor here is halfway between 1 and theta. And examples where we can get a pretty good approximation of kappa, this works really well. For examples where we can't, it works really poorly. Next, if I want my first order term smaller and the residual is already small, well, that means I can choose my, my depth mk larger. So I'm now trying to approximate my most recent residual in a larger column space. So I'm likely to be able to decrease my gain factor. And if my residuals are sufficiently small, the higher order terms don't add up in such a way that interferes with convergence, and I can get a better convergence. And so this is essentially using a dynamic choice of our depth mk. I like to do it based on the log 10 of the residual. My collaborator likes to do it based on a single switch from a small or to a larger depth. For instance, once the residual hits about 10 to the minus 2, 10 to the minus 3. These are both somewhat heuristic strategies, and sometimes you have to tune it to the particular problem, but it works pretty well. And then the last strategy here is filtering. So if I want my higher order term smaller and my depth is already greater than 1, I can filter columns of F, which is the matrix I'm using in the least squares problem, to enforce a sufficient linear independence. And so here, this is a one parameter method. I have one tuning parameter here. And so here I'm just going to discard columns of F for which the diagonal values of R divided by the corresponding norm of the column of F is less than some constant of my choosing. And here you see my cat illustrating these various strategies. We already saw the filtering picture. Here we see her doing multiple depths. She's excellent at relaxation. And she makes a really important point here, is that we can combine strategies. And this is really useful and cute. So the example here I'll use to illustrate these ideas is the P Laplacian, and specifically a Picard iteration for the P Laplacian. So for P greater than 2, this is a degenerate elliptic equation. So our nonlinear diffusion coefficient goes to 0 as the gradient of u goes to 0. So you see here our diffusion coefficient is based on the gradient of u squared. And for P greater than 2, this comes up in the modeling of piles of sand. I remember telling my students this is used for modeling sand piles, and they laughed at me, but it's actually true. And so solutions will look something like this. I think this is with P equals 6. For P between 1 and 2, it's a singular elliptic equation. And so here our nonlinear diffusion coefficient can become infinite as the gradient of u goes to 0. And this tends to be a model problem for flow in porous media. So here's our Picard iteration for a finite element discretization of the P Laplacian. Here I put in a regularization factor here epsilon that we need in the singular, but not in the degenerate setting. So we'll start with this initial guess here, and then for P greater than 2, our solutions will look something like this, and for P between 1 and 2, our solutions look something like this, where you see you have a very steep boundary layer. So here's our example of filtering. So here P is between 1 and 2. It's 1.06, so it's pretty close to 1, which can make this problem challenging from a nonlinear solver perspective. The right-hand side is just a constant function. I chose pi over here. And my regularization parameter is pretty small. It's 10 to the minus 14. I chose this value for epsilon because if I made it smaller, well, I broke it, and so this worked. So here, this is a finite element discretization, and I'm discretizing by piecewise linears. My mesh is 128 by 128. So here, SG denotes a safeguarded or strategies. And here I'm filtering based on the factor of a quarter. If this ratio between the diagonals of R and the columns of F are less than a quarter, I simply pull them out. So you pull out the column of F and you pull out the corresponding column of E. So what we see here, here's a m equals 0. This iteration isn't totally contracted. It goes up a little at the beginning and then it goes down. For n equals 2 and n equals 6, you see without filtering, it takes more than 300 iterations. With the filtering, it takes a little over 100. N equals 4 is doing something kind of interesting because it looks like it takes about the same amount of iterations, either with or without the filtering. Actually, what it's doing is it keeps filtering out the second and third column. So it's actually doing, when you filter it, it's doing like a depth n equals 2, but with older information. And that's why it doesn't converge very well. But what we see in this picture to the right are how many columns of F are actually being used at each iteration. And you see with n equals 2, it's filtering down to one column quite a lot right at the beginning of the iteration. And with n equals 6, it's also doing most of its filtering at the very beginning of the iteration and hardly any all at the end. And so this is where we see we have this linear dependence between or near linear dependence between the columns really at the beginning rather than the end of the iteration. N equals 4, it's kind of filtering through the whole time. So this is the same problem, and here we're looking at dynamic depth strategies here with n equals 8, and also using the safeguarding. So let's see here that this line here is just using a constant depth of m equals 8. The other lines here, which are all pretty close to each other, we're either using a strategy where we start with a depth of 0 and we increase like the log 10 of the residual up to a depth m equals 8, or we're doing the same thing starting with m equals 1. We're not seeing a big difference between those two, except you see here 0, it converges slower at first. And with or without the filtering, they converge at almost the same rate. So the filtering is not really harmful here. It's not really helping either. What we see on the plot on the right, though, is you see that actually columns are getting filtered out because you don't have the same number of columns always between the filtered and the non-filtered iteration. So here's a visualization of which columns of F are being used. And this is just for the constant depth m equals 8 with the filtering. And so what we see here is that it's actually the second column that's getting filtered out the most often. So it's actually your more recent information that tends to be close to your second most recent can be close to your most recent. And this is just a visualization of these ratios between the diagonals of R and the corresponding columns of F for indices 2, 3, and 4, and anything below the red line is getting filtered out. So it's really the second column that gets pulled out the most often. This example, we're using piecewise quadratics instead of piecewise linears. I got an interesting question about what happens when you use higher order elements. And one of the things that was interesting here, and this has to do with some tuning, is that first when I tried this, the filtering didn't seem to be very useful at all until I actually had to turn that factor up. And this is something we've noticed in other numerical experiments as well, is that as you use higher and higher order elements, you actually want to make this filtering factor, filtering parameter higher and higher and closer towards 1. But essentially, we see the same types of behavior with m equals 2 and 6. You get convergence about 100 iterations if you use the filtering, and it's over 300 if you don't. And here we see the dynamic depth strategies as well. And here m equals 8 with the safeguarding is actually doing the best. M equals 8 with no safeguarding is doing essentially the worst. And the safeguarded ones that have using both filtering and dynamic depth are doing nearly as well as the best one in about 100 iterations. Again, if we look at which columns of F are being used, we get that the second column is being filtered out the most often. And here, so everyone below the red line, which is now about 0.45, are being filtered out. This next example is we're doing the other regime here where we have P is equal to 6. And what's interesting here, what makes this example quite different is that the residuals start out quite large. So here the damping becomes quite important. So what we're looking at here is AD is our adaptive damping. So I chose a damping factor between 0.1 and 0.6 such that, well, we choose beta to satisfy this inequality here, and then we safeguard it. So it's between 0.1 and 0.6. If you made it too small, you wouldn't make any progress, and I just didn't want to let it become too big. So we see here, if we use m equals 4 with adaptive damping and no safeguarding, it actually doesn't converge at all. But if you apply the filtering or the dynamic depth, it actually converges quite quickly in about 100 iterations. And one of the points here is that sometimes when you just apply Anderson in its most simple sense, and even if you just increase the depth, you're not going to see convergence. But if you start to apply some of these strategies we see based on the theory, you can get a really nice convergence from it. This plot on the right, we're using m equals 8 with and without filtering and adaptive damping. So here, this pink line is m equals 8 with the filtering factor of 0.7 and a constant damping. These lines over here, we're using a dynamic depth and adaptive damping, and you see we get a much faster convergence. M equals 8, even with safeguarding and adaptive damping, it's not converging at all. I want to make a note too. I did all my finite element implementations in Phoenix here. And there's a little subtlety in that there's definitely wrong ways to interface between Phoenix and the SciPy's QR. I can't tell you precisely why it's true, but if you do this in a naive way, here, this syntax here that's commented out, this is how you would just grab the entries of the vectors, the vector of coefficients for EK and W1, and just stick them in the columns of X and F. And if you do it like this, then when you call the QR factorization, the QR will take about 10 times as long as the linear solve, which is really quite bad. If you use this syntax here as backend type, it takes less than 1/10, really closer to 100th of the time for the linear solve, which is what you'd expect. I'm actually not entirely sure why this works or what goes wrong here, but it doesn't have to do with sparsity because these vectors aren't sparse. But this is just a note to Phoenix users. There is a right way to do this, and that's basically it. So this new theoretical understanding helps us guide the design of methods with adaptively updated filtering, algorithmic depth, and damping. But remember that if Newton is working, just use it. This isn't going to help you. But if Newton is diverging or is undesirable to form a Jacobian, then applying Anderson can really give you either Newton-like or nearly Newton-like performance at really minimal cost. It's worth trying. Recently, we're working on applications to non-Newtonian fluids. We've been looking at Bingham fluids lately. One of the interesting things here is we're looking at these regularized Bingham fluids. And so these are non-Newtonian fluids that act like a fluid under high shear stress and act like a solid under low shear stress. A nice example is mayonnaise, if any of you make sandwiches. So if you spread the mayonnaise, this is under high shear stress, it's spreading like a fluid. But when you take the knife away, you still see the knife marks in. And so it's acting like a solid under low shear stress. Also, wet cement is also such a fluid, as is cake batter and toothpaste. And we're also looking at this in terms of another type of non-Newtonian fluid, a grade 2 fluid, which are some examples are motor oil and gelatin. And so what we see with the Bingham fluids, where we have to use this regularized formulation, is that without the acceleration, as the regularization parameter goes to 0, the number of iterations to solve really increase. With the acceleration, they don't. Similarly, with these grade 2 fluids, if we do this in a contracting duct, there's a reentrant corner where actually our auxiliary variable is singular. And if we use the acceleration, we can solve this on much finer meshes than we can without the acceleration, where first of all, the number of iterations increases very rapidly as we refine the mesh, and then it just fails to solve altogether. So it's really a kind of a nice enabling technology in these situations. In process, we're trying to put these ideas together to create a more robust globalization strategy, and this is work in progress. And that's it. And thank you. And I was standing over there and ignoring the chat entirely. But nobody put anything in the chat, so it's okay. Does anybody have any questions? Yes.
Yeah, so I didn't quite see how you would fit the concept. There is another possibility, which is to use just regularization.
Mm-hmm. Yeah, so our first thought was just to use a truncated SVD, and it you can do it at low cost if you do the QR and then just take the SVD of R. It really doesn't do any better than this filtering strategy, and it's harder to analyze. Okay. Yeah. Oh yes. Sorry. The question was, well, first of all, what exactly are we doing with this filtering? And the second question was, why not just use a truncated SVD or a Tikhonov regularization? So there actually is a body of work using like a Tikhonov type regularization, and what's found is that they're not getting enough accuracy out of it, and so they're not really happy with it. And essentially they're doing it is they're penalizing against making the optimization coefficients too big. So it accomplishes the same strategy in terms of controlling the size of the coefficients, but it deteriorates accuracy. And again, we wanted to look at the truncated SVD, but it just became less interesting when we compared the two and we saw that this was actually working just as well, and we already knew how to analyze it. I think the last part of your question is what exactly are we doing with the filtering? Right, so what we do is you compute our QR factors, and then we just compute this ratio of the diagonal entries of R over the corresponding norms of the columns of F. If that's bigger than what we want, then we just, if that ratio is smaller than what we want, is we just remove each corresponding column of F and column of E, and it just filters it out of the iteration. Does that make sense? Mm-hmm. Yeah.
I have a follow-up on that. I remember a paper recently, maybe not so recently, but by Tim Kelly and Simpson, and I think they I don't remember what context of this is, but they talked about using subset selection instead of TSVD as a possibility. And I don't know if you consider something like that as well. If it makes any sense. I have no idea.
I think this is another way of thinking about that. What was interesting about this is we hadn't intended to design a filtering strategy here. What we did is we came up with this analysis, and then one of the reviewers in the paper said, like, well, what's the big deal? Why do you claim that, like, assuming that you have this this condition, why do you claim that that's better than assuming the optimization coefficients were bounded? And I had to admit it was a really good question. And I thought about it. I thought, well, this we can safeguard. And then I tried it, and it worked really well. But I have seen other approaches to how do we, I think Homer Walker has some work on this, which columns do you pull out if you're having a problem with the condition of this matrix?
You can also use the randomized version. Randomized linear or even randomized QR.
But the question is, why would you want to? Because you don't have very many columns.
Okay, if you don't have an issue with the size.
Yeah. I mean, if your problem was such that, and there are such problems that you really can use a lot of columns, and then this is a good idea to use the randomized version. But generally what we find is that this is a rare circumstance, because then we would really have the higher order terms piling up. And that's what you want to guard against, unless your residual is really small. So at some point, once your residual is small enough, you've only got so many iterations left before you're actually converging. And I think that's the reason we might not necessarily want to do that. But I'm sure there's an application out there where this would be useful and would be a great idea.
We're actually responding to that. I'm actually exploring this for the context of optimization. Right? So when you have the pi equals to x plus f, so the f there is actually a gradient of some objective function that optimized. So I want to have the gradient equal to 0. So in that case, we're actually exploring using maybe the m equals to 30 or 50. So in that case, that is really big.
I mean, is that really big, like 30 or 50? I don't know.
Run an optimization loop that you have to optimize over, like, I don't know how many millions of parameters and so on, that it piles up.
I guess big is a state of mind. Yeah.
We're talking about the sub m side, right?
Yeah.
Yeah, you have like a linear, so super linear convergence if m is very small. That you're using type convergence to require an m that's large.
Yeah. So really, what you get is this much steeper slope on your linear convergence, but usually that gets you to convergence fast enough.
Yeah. The one thing is that we want to get a correct understanding of your message in the final slides. So you said that if you lose at works, then lose.
Yes.
Does it mean that usually if my optimization, if my optimization is actually already working, then maybe there's not much hope that I can get better exploring X and so on?
If you already have quadratic convergence, you're not going to help it with Anderson.
No, that's not what happens in optimization context. So.
Okay. If you have linear convergence, then there's a good chance you can improve it with Anderson. But you probably have to implement it correctly to actually see that.
No,
sometimes
the optimizers that we're using actually is first order. It's never going to the second order. So the convergence and both will be linear, but sometimes it's actually just one of a square root of 2.
Then it might be worth a try.